Okay, welcome to Lesson 1, Ligand Substitution. We're going to start with a review of ligand substitution kinetics that we talked about in class before break. Then we're going to cover the Eyring equation and introduce the first homework that covers the Eyring equation. Okay, so the first type of ligand substitution we talked about is associative ligand substitution. This is seen in square planar complexes. And the rate law is a rate constant times the concentration of the starting complex and the incoming ligand. We see an intermediate that's got a pseudo-trigonal bipyramidal geometry as the new ligand comes in, and then we lose one of the original ligands to make our new square planar complex. There's a slide coming up that reminds us about the trans effect for predicting the geometry of the final complex. The dissociative ligand substitution reaction is usually seen in octahedral complexes. So we lose a ligand to form an intermediate that's square pyramidal, and then we gain the new ligand, which is a faster second step, and we have our new octahedral complex. The rate law shown there is a general rate law for that type of substitution reaction. Most chemical reactions are actually doing an interchange type of reaction. You can have interchange associative or interchange dissociative. That just depends on how much bond making or bond breaking is taking place at the transition state. This is relatively complicated. We won't be covering it in Chem 104 beyond this, but most chemical reactions are not purely dissociative or purely associative. Okay, so general features of octahedral ligand substitution. This is a general rule, but we will, for Chem 104, octahedral complexes will lose a ligand first and then gain a new ligand. Octahedral complexes are coordinatively saturated. They don't have any more room around the metal to add another ligand, and so it's easier to lose a ligand and then gain one from the square pyramidal complex. I had to do a homework on calculating delta CFSE for octahedral complex turning into a square pyramidal complex. This answer key is now posted on the resources for March 9th class as a PDF. So take a look at that homework and make sure you understood what you did. I have your homeworks and I'll scan those and get those to you sometime soon. Remember, the crystal field activation energy is an adjustment to the activation barrier for the ligand substitution. A delta-delta CFSE of about 2.5 kcals per mole is approximately a 70-to-1 relative favorability of the chemical reaction. We did this in class. This is just a review. And inert metal complexes are those that have D3 and D6 configurations. Trans effect and the order of trans effect. This allows you to predict the stereochemistry of a substitution reaction. So if you have a halide relative to an ammonia, the halide has a stronger trans effect, and so a ligand that is trans to a halide is more likely to be lost. There was a homework that was due right around spring break that only one person did. I ended up not grading it. So take a look at the homework key, which is in the resources for March 11th. My video is blocking that, but it's in the March 11th folder. And take a look at that answer key to understand how you can use the trans effect to predict stereochemistry. Okay, moving on to the Eyring equation. This is an equation that you can use to determine activation parameters, delta H and delta S of activation for a chemical reaction. This is how we determine chemical mechanisms. It's one of many ways. But you measure the reaction rate at different temperatures, and then you extract those activation parameters from the fit. So there's the exponential form, which is this equation over on the left. You can extract delta H and delta S from the exponential fit. The linearized form is much easier to use, and that's the form that we'll use in Chem 104. You plot the natural log of the rate constant versus temperature. Sorry, the natural log of the rate constant divided by temperature versus 1 over temperature in Kelvin. The slope is minus delta H double dagger over R, and the intercept is blocked, but this PowerPoint is on Sakai. So the intercept is the sum of delta S over R plus the natural log of KB over H. When I learned to do the Eyring equation, people always used to say, oh, there's an error because you have to extrapolate this linear fit a long way to get to the origin, and so therefore the delta S of activation isn't known as accurately as the delta H of activation. This is not true. Take a look at this article. There's a link posted from one of the resource pages before spring break. So if you're interested in seeing why that isn't true, you can take a look at that article. And one thing that linear fits allow you to do is you can tell if a line goes through a series of points by eye pretty easily. It's extremely difficult to determine whether or not something fits an exponential fit by eye. And that same article talks about proper weighting of exponential fits. If you don't use proper weighting of your data, then you're not going to get the right fit. I'm not going to talk more about that in class. If you have questions, come to office hours and we can talk more about it. But basically, if you ever need to fit an exponential data, make sure you understand how your program fits the data and weights the data appropriately. I figured out how to do this in an Igor over break, so if you're interested, I can talk more about that individually. What do these activation parameters mean? So the enthalpy of activation, delta H double dagger, is really only useful if it's large, so 50 to 100 kilojoules per mole or 12 to 25 kcals per mole. If you have a lot of bond breaking at the transition state, that indicates a dissociative mechanism, and delta H double dagger is going to be large. Bond making at a transition state is suggestive of an associative mechanism. Delta H double dagger is less large. That's a little bit trickier to use. The more useful activation parameter is delta S of activation, and large values either greater than positive 20 kilojoules per mole or less than negative 20 kilojoules per mole, or 5 kcals per mole. That's a very meaningful number, and if delta S is larger than positive 20 kilojoules per mole, that suggests more disorder at the transition state. There's an increase in entropy at the transition state, suggesting a looser complex and a dissociative or an interchange dissociative mechanism. If delta S is less than 0, delta S of activation is less than 0, that suggests an ordering at the transition state on the alignment of paths, suggesting an associative type of mechanism. Okay, let's look at the problem set, the homework. There's a PDF of this on Sakai, but it's the same equation here. This is a chemical reaction where you take a molybdenum oxo-tris amide complex and you heat it for 5 days at 65 degrees. You lose a t-butyl radical and you get the oxo-imido complex. There's some numbers plotted there, temperature in degrees C, and the rate constant of the reaction that was extracted. So let's use the linearized form of that equation to determine delta H and delta S double dagger, and then you could use that information to determine more about the mechanism. And if you're curious, take a look at that Jacks paper from 1998. You may know one of the authors on that paper. Kb is Planck's constant, so there are the units in Planck's constant. But if there's anything I know about Planck's constant, it's just I'm so sick of Planck's constant nagging over and over again that the speed of light just isn't going to change. Blah, 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 blah. Sorry about that. H is Boltzmann's constant, so there are the units and the number. And K is the rate constant, and make sure to use the right value for the gas constant in joules per mole Kelvin. So if you do all that, you'll get the right answer. So what I want you to do is, for the homework, plot that data and make sure that you can extract the correct delta H and delta S of activation. Common mistakes, students forget to convert temperature to Kelvin, so do that. And then the labeling of the units on the rate constants. That first point is 0.586, and we've divided out 10 to the minus 5. So that first data point is 0.586 times 10 to the minus 5th per molar per second, or 5.86 times 10 to the minus 6 per molar per second. So play around with that. The answer key is on Sakai, so you can check your work to make sure that you got the correct activation parameters. And let me go back 2 or 3 slides because I forgot to say one thing when I was here. Oh, here, on the right, under the linearized form, the slope. Oh, I did talk about this. So, okay, we're done. Have fun with this homework.